Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to the subject Electromagnetic Field Theory. We are with chapter number 10, that is the uniform plane waves. In this chapter we started with the first topic, that is Maxwell's equation into the phasor form. Previously we have seen the Maxwell's equation summarizing the electrostatic fields as well as the steady magnetic fields in the form of 4 equations into the time domain. For convenience and further derivations, we have the Maxwell's equation into the phasor form now. From the Maxwell's equation, now we are successful to derive the wave equation, where we get the information regarding the time variations of the electric field intensity and the magnetic field intensity vectors, along with their variations with respect to the space parameters. In Cartesian coordinate system, we say the parameters are x, y, z. Now from the wave equations for general conducting medium, we have the solution of that particular wave equation, and further we have the parameters that are giving us the information regarding wave propagation into the general conducting medium, that are alpha, that is attenuation constant, beta, the phase shift constant, propagation constant, gamma, the intrinsic impedance eta, velocity of propagation v, along with lastly the wavelength of the uniform plane wave, we can say represented by lambda. Now we have seen the wave propagation into the perfect dielectric medium, into the perfect conductive medium. We have solved problems based on to the perfect dielectric medium also. Now the topic is wave propagation is in the good dielectric medium. Further we shall be taking the topic, that is wave propagation into the good conducting medium. So let us first of all see how exactly the wave propagation for good dielectric medium or good conductive medium we say. So let us take the topic. Now according to the Maxwell's first equation into the phasor form, we can write del bar cross of h s bar. Here h suffix s is for representation of the phasor. So it is given by, in the time domain we have j bar plus del d bar by del t. J bar, by using the Ohm's law into the field theory, we write sigma into E s bar. And the second term, that was del d bar by del t into the time domain or phasor form, we have j omega epsilon E s bar. So now this first term is actually the conduction current density in the vector form, and the second term is again the displacement current density. Both are the current densities. This is because of the actual conduction of charges like the free electrons, we can say, and this is because into the non-conductive medium because of the electric flux, you can say. So it is a displacement kind of thing. Hence JC bar and JD bar is the thing. Now if we take the ratio here, so we shall be writing sigma ES bar divided by J omega epsilon ES bar. So this ratio is actually JC bar by JD bar, or only magnitudes if we say. So these ES bar shall be getting cancelled, and simply JC by JD we shall be left with, for magnitudes if you take, it will be simply sigma upon omega epsilon. J also we have to neglect, as it is a representation of the imaginary portion only. So real part divided by the imaginary part is giving us the ratio sigma divided by omega epsilon. Now if this ratio holds the value 1, we shall say that JC is equal to JD. It means the conduction current density is actually equal to the displacement current density. Now the differentiation we can make into the conductors and dielectric. When the conduction current density holds more value than the displacement current density, we can say the conductivity is more. Therefore the material under consideration is a conductor. If we have JD more than the JC, it means the displacement current is more in the magnitude with respect to the conduction current. So that means that the particular material into the consideration is a dielectric medium through which only the flux can pass. Therefore, here we can have JC is equal to JD being the demarcation line which decides whether the given material is of conductive type or dielectric type. Hence, if we take the cases JC greater than JD, we shall be simply writing it is conductive medium, and for this conductive medium, as we have taken JC upon JD is equal to sigma upon omega epsilon, so we shall say that for the general conductive medium, sigma upon omega epsilon holds the value that is greater than 1. Or in reverse way, if we take JC less than JD, so that time we shall be in general say this will be dielectric medium, and this shall imply that sigma upon omega epsilon holds the value that is less than 1. Now we can have more categorization as good conductors and good dielectrics. So that time if we have the ratio or the comparison of conduction current density with the displacement current density as JC is very greater than JD. So that time the ratio will be sigma upon omega epsilon, the term that is very greater than 1. So in this case we say that the material is good conductor. Now if we take the reverse case, JC is very less than JD. So it means the displacement current is very much higher with respect to the conduction current. So this implies the ratio sigma upon omega epsilon that is holding the value very less than 1. So this time we shall call that the material is good dielectric medium. So with the ratio or with the value that is sigma upon omega epsilon, where sigma is conductivity, omega is angular frequency of wave, and epsilon is permittivity of the medium, we can get the information whether it is of conductive nature or dielectric nature, or if it is having very much higher value than the 1, so we shall say it is good conductive material. If it is having very less than value than 1, so it will be good dielectric medium. If it is equal to 0, we shall say that it is a perfect dielectric. If this value holds equal to infinity, very much higher than 1 and equal to infinity, we shall say that it is a perfect conductor. But if you take materials into the consideration, no material is a perfect conductive one and no material is a perfect dielectric one. Practically the materials are having finite conductivity. So this ratio, that is sigma upon omega epsilon, will be helpful to us to determine the nature of material. Now the JC bar and JD bar both are the current densities. So current density initially we used to represent by J bar, and now we know that JC bar plus JD bar, this way we can resolve the vector current density. So in general, if I draw J bar with this vector representation, I must write into the phasor form, it is JS bar. So if the resolution into the two components is there, these two components should be making 90-degree angle with each other. So that time JC bar or JD bar we can show like this. So JD bar, if I show, so it is having the representation into this diagram where the resolved components are perpendicular to each other. The JC bar I have to show with this line. So these lines are parallel here. Now this is the first current density JC bar, or the phasor as I have represented for J bar. So this is JC suffix S bar, and it is given by sigma into E S bar right from the Ohm's law. And this one that we shall be writing, it is JD bar equal to J omega epsilon into ES bar. So these two make 90-degree angle here. Now in this particular diagram, if you take the angle that the displacement current density vector makes with the total current density. So the angle we shall be representing by phi here. So now if we say that the phi is increasing, so that means the phi increasing will reduce the length of this vector, or in turn increase the length of this particular vector. So it means the GD, that is displacement current density, is reducing, the conductivity, the conduction current density is increasing. So if the conduction current density increases, so that time the I square R type of losses also increases, that will be taking into the medium of propagation. If the phi value will reduce, so that time the JD bar will getting increased and decreasing the JC bar. So for decrease into the value of phi, we can say that the conduction current or the conductivity reduces, also reducing I square R losses. So here we can say phi is the angle giving us information regarding the losses to be taken place into the medium in which we have the wave propagation. So as it is giving us the information regarding the losses, we shall be terming a loss tangent term. As we pronounce tangent right from the trigonometry for the angle phi, we shall be taking the tangent value. So tangent of this particular phi will be opposite side upon the adjacent side. So opposite side into the magnitude will be that of the JC bar magnitude, and the adjacent side will be of that of the JD bar magnitude. Hence loss tangent, or if I represent it by tan phi, so this is nothing but sigma upon omega epsilon, that we have used to categorize the material, whether it is conductive or dielectric, good conductive or good dielectric medium. Now our topic is wave propagation into the good dielectric medium. So this exactly we start with this one. So now for good dielectric medium, we shall put the loss tangent, that is sigma upon omega epsilon, to hold very less than 1 value. Now we have to cross check the values of alpha, beta, eta, velocity v and lambda for the given medium. Now we know the general expression of alpha into the good conducting medium, general conducting medium. Alpha is given by omega under root of mu epsilon divided by 2. Inside the bracket again we have under root, it is 1 plus sigma square upon omega square epsilon square, it is minus 1 here. It is always given to us into the Nepers per meter. So now for this alpha value, as we are having the medium to be a good dielectric medium, we substitute sigma upon omega epsilon value is very less than 1. So upon this particular substitution, this particular bracket, so that is the square of this. So if the quantity is having less than 1 value, that means 0 point something, and that too 0.000 and something, so that time certainly the square of that particular term will be again having smaller magnitude than the ratio sigma upon omega epsilon. So very smaller value will be added to the 1. Already it was very less than 1. Hence we shall be using here the binomial expression to represent this particular under root. So according to the binomial expansion formula, it is binomial expansion formula, the square root term we shall be representing 1 plus, it is sigma square divided by omega square epsilon square. This bracket I give the power 1 by 2 to represent the square root. So according to binomial expansion, it is 1 upon 2, it is 1 to the power 1 by 2 plus, here it is 1 by 2 into 1 to the power minus 1 by 2 into sigma square omega square epsilon square to the denominator plus some higher terms. Already we have selected sigma upon omega epsilon very less than 1. Into the second term we have the square of that one. Into the higher term, we shall be having the cubes, we shall be having the powers 4, 5 and so on. Therefore, here we have to neglect all the higher terms, and this square root, that is 1 plus sigma square upon omega square epsilon square to the power 1 by 2, we shall be approximating to 1 to the power 1 by 2 will be 1, plus it will be sigma square upon twice omega square epsilon square. So 1 upon 2 is multiplied here, neglecting the higher terms here. Therefore, this particular substitution, in place of this, we substitute into the general formula or general medium. So the alpha will result to us, alpha will be given by omega under root, here we have mu epsilon divided by 2, in multiplication with it will be sigma square upon twice omega square epsilon square. Because whatever the 1 we had, so that will be subtracted with the 1 and it will be resulted into this much. We can again have the simplification of alpha, so it will be sigma divided by 2 under root mu upon epsilon. So as alpha is there, we again give the unit Nepers per meter. So for a good dielectric medium, the attenuation constant is given by the new and simplified formula. It depends only on the conductivity value, permeability value and the permittivity value. Sigma upon 2 under root mu by epsilon. So this way we have taken the new formula of alpha for good dielectric medium. Now the formula for beta is to be determined. For general conducting medium, beta is given by the formula omega under root, here we have mu epsilon divided by 2. Inside the bracket, we again have the under root 1 plus sigma square upon omega square epsilon square. It is plus 1 here. Here also we will be trying to represent sigma upon omega epsilon will be very less than 1. So here again we shall be using the binomial expansion and will represent, it will be 1 plus sigma square omega square epsilon square to the power 1 by 2. So this under root term, that is the first term from this curly bracket, that we are representing by binomial expansion 1 to the power 1 by 2 plus 1 by 2 into 1 to the power, it will be 1 by 2 sigma square upon omega square epsilon square plus the higher order term. Higher terms simply I write. So now we know that the very less than 1 value, if squared and taking the powers of 3, 4 and so on, we shall be getting very lesser magnitudes to the higher order terms. Therefore, this also we approximate to 1 plus, it will be sigma square upon twice omega square epsilon square. So this we are going to substitute in the term of the first term of this particular curly bracket. So beta gives us, beta will be equal to omega as it is. Here we have the under root sign, mu epsilon divided by 2. In the curly bracket we put 1 plus sigma square upon twice omega square epsilon square plus 1, it was already there, completes the square bracket. So in place of this we have substituted and we have obtained this particular one. So 1 plus 1 will be equal to 2, and finally the beta we can have into the modified representation. So beta will be equal to omega under root mu epsilon inside the bracket 1 plus sigma square upon 8 times omega square epsilon square. So from this particular bracket we have taken 2 to be the constant outside to get it cancelled here. So omega under root mu epsilon, here we will be left with 1 plus sigma square upon 8 omega square epsilon square. As this is beta, we put the unit, that is radians per meter. So this way the simplified formula for attenuation constant alpha and now the phase shift constant beta we have derived. Now, along with alpha and beta, we have many more parameters like the intrinsic impedance eta. So, the general expression for eta into the general medium, that is given by under root mu upon epsilon in multiplication with 1 divided by under root 1 minus j times sigma upon omega epsilon. Now here also the term that is sigma upon omega epsilon, what we have termed to be the loss tangent, is present, and loss tangent sigma upon omega epsilon we have selected very less than 1, or the medium being the good dielectric medium. So here we shall be representing it under root mu upon epsilon, and this particular bracket will represent the denominator square root term. It is 1 minus j times sigma upon omega epsilon to the bracket. I put the power that is minus 1 by 2 as it was into the denominator. So again here we'll be having the binomial expansion. The binomial expansion will give us this particular term, so that I write very separately. So it will become 1 minus j times sigma upon omega epsilon to the power minus 1 by 2 will be 1, plus it will be minus 1 by 2 in multiplication with j sigma upon omega epsilon plus the higher order terms. So we know that sigma upon omega epsilon very less than 1, the higher order terms will again result into the very lesser values. So here also we approximate it to the first two terms. So it will be 1 plus j times sigma upon twice omega epsilon. So this we will be having into the substitution for the eta formula. So this complete bracket to the power minus 1 by 2, we shall be writing this one. So this gives us the resultant. So resultant eta will be equal to under root mu upon epsilon in multiplication with the bracket 1 plus j times sigma upon 2 times omega into epsilon. So as this is intrinsic impedance we measure into the ohms. Therefore, the intrinsic impedance is given by this particular formula under root mu by epsilon in bracket 1 plus j times sigma upon twice omega epsilon. So at this point we are covered with determination of the formulae for attenuation constant alpha, the phase shift constant beta, and the intrinsic impedance eta. Now we shall focus on what would be the velocity of propagation of the uniform plane wave into the good dielectric medium. Now the generalized formula of V we have obtained by taking the ratio of angular frequency omega with respect to the phase shift constant beta. So this becomes omega divided by, it will be omega under root mu epsilon in multiplication with 1 plus sigma square upon 8 times omega square epsilon square. This is in meter per seconds. So into the denominator beta we have substituted what the formula we have derived for the same good dielectric medium. So here we have the sigma upon omega epsilon squared, and it is a part of this bracket and into the denominator. So now this bracket we represent again by using the binomial expansion. So it will be 1 plus, we have sigma square divided by 8 omega square epsilon square. So I write the power of this particular bracket equal to minus 1. So using the binomial expansion we have the first term 1, the second term it will be minus 1 in multiplication with sigma square upon 8 times omega square epsilon square plus the higher order terms. Higher terms I write here. So here also as we have sigma upon omega epsilon very less than 1, the higher order terms are really reflecting the very less magnitudes, hence neglecting all the higher order terms. The first two terms we shall be approximating, and here the bracket that is 1 plus sigma square upon 8 omega square epsilon square to the power minus 1, we shall be having 1 minus, it will be sigma square upon 8 times omega square epsilon square. Therefore, the velocity expression that it was for the general conducting medium will modify to 1 upon under root mu epsilon in multiplication with this particular bracket term 1 minus, it will be sigma square upon 8 omega square epsilon square. So as this is velocity of propagation, we give the unit that is in SI system of units meter per seconds. So now we have checked for the attenuation constant alpha, the phase shift constant beta, the intrinsic impedance eta, and the velocity of propagation v for the wave propagation into the good dielectric medium. Now the last expression will be for the lambda. The lambda expression we can obtain by taking the ratio of velocity of propagation to the frequency f. Hence, we shall be substituting the above expression for the velocity and it will be divided by simply the f. Therefore, the lambda will be given by 1 upon I mention f into under root mu epsilon. And in the bracket again we have 1 minus sigma square divided by 8 times omega square epsilon square. So as lambda is the measurement of distance, it is the distance covered in one wave cycle, it is measured into the meters. So the last parameter I outline here. So here we are finished with the wave propagation into the good dielectric medium. In this topic, we started with the loss tangent, that is giving us the information what losses may occur while the wave propagates into the given medium, and with that particular loss tangent ratio, that is in terms of sigma upon omega epsilon, we have all these formulae for alpha, beta, eta, v and lambda. In the next video, we shall be taking into consideration the wave propagation in good conducting medium. So for getting such more information with this subject electromagnetic field theory, you can subscribe to Ekeeda channel. Thank you.